All right, welcome to this explainer. Today we're unpacking a truly foundational piece of machine learning history. We are looking at the landmark paper, Algorithms for Non-Negative Matrix Factorization. This was published back in the year 2000 by Daniel Lee and Sebastian Singh. Before this paper dropped, teaching a computer to actually understand complex data was, well, it was often a really messy mathematical compromise. But Lee and Singh, they introduced a perspective that literally revolutionized how algorithms learn the underlying parts of data. It basically made the invisible structures visible. So let's just dive right into this.
Here's our roadmap for today. We're going to start with the conceptual brilliance of the power of parts, then unpack the core data matrix equation and see exactly how the algorithm measures its mistakes. After that, we'll hit the multiplicative update rules, and finally, the mathematical engine guaranteeing the whole thing actually works. Okay, section 1, the power of parts. Let's set up the fundamental problem researchers were facing here. Imagine you hand a computer thousands of images of faces, or maybe thousands of text documents, right? And you give it absolutely no labels. The core question is this: how do unsupervised learning algorithms actually understand complex, multivariate data? How in the world do they make sense of all that information and find those hidden patterns without a human sitting there guiding them? To really appreciate the solution, we kind of have to look at how older algorithms worked. For a long time, the go-to was stuff like principal components analysis, or PCA. Now, PCA enforces this weak orthogonality constraint. It allows both positive and negative numbers, meaning it uses cancellations to generate variability. It's kind of like trying to draw a face by taking an average blurry blob and then subtracting a nose to make eyes. It's highly distributed, sure, but it is super unintuitive. Then, on the other extreme, you've got vector quantization. This is a hard winner-take-all constraint. It forces data into these mutually exclusive prototypes. You're either in group A or group B, zero nuance. But non-negative matrix factorization, or NMF, does something completely different. It imposes a strict non-negativity constraint. Because you can't use negative numbers, you literally cannot subtract. You can only add. And this forces the algorithm to learn a parts representation. Think of it like Lego blocks. You build a complete face by adding a specific nose block, an eye block, and a mouth block together. It just makes sense. Moving on to section 2, unpacking the data matrix. Let's shift from that Lego concept into the core math making this parts-based representation possible. And honestly, the whole crucial point comes down to this one elegantly simple equation. V is approximately equal to W times H. That's the whole thing. That is the central equation of non-negative matrix factorization. Just let the absolute simplicity of that sink in for a second. We are essentially taking one giant complex thing and approximating it by multiplying two smaller things together. So let's break down what each piece of this puzzle actually is. Our matrix V here, that's the original data. Let's say it has n rows and m columns. So maybe that's m different images, each with n pixels. Now we want to factorize this into our two smaller matrices, W and H. The matrix W contains the optimized basis factors. These are our parts, right? Our Lego blocks. And matrix H, that contains the weights. Think of H as the instruction manual telling us exactly how many of each block to use for every single image. And the real magic rule here, every single number across V, W, and H must be 0 or positive, because everything is strictly non-negative. Data vectors in V are approximated purely by linear combinations of the parts in W, weighted by H. You only add, you never, ever subtract. All right, section 3, measuring the error. We are getting into the engine room now. How does the algorithm actually know if it's picking good parts and the right weights? Well, to solve V approximately equals WH, we obviously need a mathematical way to measure the error between our actual data and our current approximation. Basically, before the algorithm can magically compute these perfect factors, it needs a cost function. It means a scorecard telling it exactly how well, or how terribly, it's doing at recreating that original matrix. So Lee and Sung analyzed two different cost functions for the scorecard. The first one is Euclidean distance. You probably know this as your conventional least squares error. It's symmetric, meaning the distance from A to B is the exact same as B to A, and it's lower bounded by 0, so a perfect reconstruction just means 0 error. Simple enough. But they also introduced a second measure, which they called divergence. Now, this one is based on Kullback-Leibler relative entropy. It's also lower bounded by 0, but interestingly, it is not symmetric. You might be wondering, why use this? Well, divergence turns out to be incredibly useful when your data can be thought of as normalized probability distributions. Depending on the exact nature of your data, one of these scorecards might lead to a way better, much more meaningful parts representation than the other. Which brings us to Section 4, multiplicative update rules. We know what we want to do, we know how to measure our mistakes, so how do we systematically fix those mistakes? Now, you might be sitting there thinking, hey, we've got an error function, why not just use standard gradient descent to minimize it? Well, as the authors point out, gradient descent relies heavily on step sizes. And that gets tricky. If you pick a step size that's too small, your algorithm literally takes forever. Pick one that's too large and it overshoots the minimum entirely and fails. Having to tune this can be a massive headache, especially when you're dealing with huge data sets. So NMF requires a smarter, significantly more reliable update method that naturally respects that strict non-negativity constraint we talked about. So instead of adding or subtracting a gradient step, the authors use this brilliantly elegant multiplicative update loop. Here's how it works. Step 1, take your current guess for matrix W or H. Step 2, multiply it by a specific factor that's derived entirely from the quality of your current approximation. Step 3, repeat. Literally, that's it. You just keep multiplying. And the math completely guarantees that with every single multiplication, your approximation improves. There are a few key reasons why these update rules are just so powerful. First off, they are incredibly easy to implement in code. We are talking just a few lines of basic matrix multiplication. Second, it completely sidesteps that annoying step size sensitivity we just talked about with gradient descent. Third, if your approximation happens to be absolutely perfect, the multiplicative factor mathematically becomes 1, or unity. That means the values just stop changing entirely, which is exactly what you want. And finally, the authors actually show that this is a cleverly disguised form of diagonally rescaled gradient descent, where the rescaling factor is optimally chosen on the fly to guarantee convergence. It really is this perfect compromise between speed, theoretical soundness, and just sheer ease of use. All right, final section. Guaranteeing convergence. Now, if you're mathematically inclined, I'm sure you have some natural skepticism right about now. The big lingering question is this. How do we absolutely guarantee these iterative multiplications actually improve the approximation every single time? Like, how do we know for sure we won't just get stuck in some endless loop or that our error won't randomly spike back up? To actually trust the algorithm, we need a rock-solid scientific proof. To prove this, we can look right at the graph here from the original paper. See that bottom curve, f of h? That is our actual error. Obviously, we want to find the absolutely lowest point on that curve, but directly minimizing f of h is mathematically tough. So the authors define an auxiliary function. That's the top curve you see, g. Notice how g kind of acts as a roof over f. It touches f perfectly at our current guess, but everywhere else it sits above it. The absolute genius of this is if we find the minimum of that auxiliary roof, we are mathematically forced to push our actual error curve downwards. This beautiful bit of geometry basically translates the dense mathematical lemmas of the paper into pure intuition. The authors note this is highly analogous to the famous expectation-maximization, or EM algorithm that's used in statistics, because G acts as this strict upper bound, and our multiplicative update rules systematically minimize G. Iterating those updates is mathematically guaranteed to converge to a locally optimal matrix factorization, meaning the error can never ever go up. It only goes down, or it stays flat. I really want to conclude with this quote from Lee and Sung right at the end of their discussion. They wrote, "The update rules themselves are extremely easy to implement computationally and will hopefully be utilized by others for a wide variety of applications." I mean, this is basically the mic drop of the paper. They took a highly complex, non-convex optimization problem, fully proved its monotone convergence using these advanced auxiliary functions, and then just packaged the whole shebang into an update rule that a student could code up in 5 minutes. Which leaves us with one final provocative thought. Whether you are out there analyzing facial images, text documents, or even astronomical data, what hidden latent structures will your data reveal when you strip away the subtractions and strictly force your algorithms to build only by adding parts? Just think about how this simple constraint of non-negativity might completely illuminate the true building blocks of your own complex datasets. Thank you so much for joining me on this explainer. Keep learning and keep building.